You're looking at one of the strangest things that water does, and it's happening every time that you turn on the faucet. It's called surface tension. Water molecules pull each other in every direction, but at the surface, there's nothing pulling from above. So, the surface molecules grip each other sideways harder. That sideways grip acts as a stretched skin. It's strong enough to hold up a paperclip or a bug, even though both are denser than water. Here's the thing about that skin. It costs energy to make. Every bit of surface area is energy the liquid would rather not spend. So liquids are lazy. They want the smallest surface area they can afford for a given volume. Take a cylinder of water, radius r, length l. Now imagine that same volume of water broken into a chain of equal-sized spheres. The drops have about 11% less surface area than the cylinder. Same water, less skin, lower energy. So where does that 11% come from? 4 steps. First, the water doesn't disappear when the stream breaks up. So the volume of all the drops has to equal the volume of the cylinder. Second, we need to know how many drops we get. Plateau and Rowley showed that a stream pinches off about once every 2 pi big R along its length, once per circumference. So n, the number of drops, is the length of the stream divided by that wavelength. Plug that into the volume equation, solve for the drop radius, and you get a clean result. Each drop is about 1.68 times wider than the original stream. That matches what you see in the high-speed footage. And finally, divide the total area of the drops by the area of the cylinder. Plug in n from step 2 and r from step 3. Combine into a single fraction, and the structure becomes clear. The L on the top cancels the L on the bottom, and r squared cancels with 2 pi r squared, and you're left with about 0.89. The drops have 89% of the original surface area, no matter how big the stream is or what fluid it's made of. So, if the stream can break up, it will. But how it breaks up depends on the liquid. Here are 3 of them, all filmed at 2,000 frames per second. Water breaks up cleanly. Watch the ripples grow, the neck thin, and the drop pinch off into a near-perfect sphere. You'll see tiny satellite droplets between the main ones, leftovers from the neck snapping back. Isopropyl alcohol has a lower surface tension than water, about a third. Their storing force is weaker, so the drops come out smaller and more regular. Dish soap is a slow one. It's much more viscous, and viscosity fights the pinch. It drags the neck out into long, thin filaments before it finally lets go. Same physics, just stretched in time. Across all 3, there's a pattern. A stream pinches off when a ripple along its surface has a wavelength bigger than its circumference, a little more than 3 times its width. Below that, surface tension smooths the bump out. Above it, the bump runs away and a new drop is born. This is called the Plateau-Rowley instability. It's why faucets drip, why rain forms spheres, and why your inkjet printer can fire out millions of identical droplets a second, all from a little liquid trying to be a little lazier.